Yeah, yeah, yes, yes.
Yeah, yeah. Thank you. So I will let me share my screen. Is the screen visible now? My screen.
Yes, sir. Yes, sir.
Yeah, so thank you, Gattu sir, for giving a nice introduction. And it is actually an honor for me to come and discuss about one project that we have done at NIT-Rourkela. So I just want to know the audiences are all master students or
There are few faculty
faculty
and
members also? Okay.
there are PhD students and
Okay.
some industry
Okay.
professionals.
Right, sir. Right. So I want to come to that slide first. If you see this left side one figure, it is a dashboard of a car where we have a lot of information we get, the speed of the vehicle and many other things, fuel, how much fuel is left, fuel gauge is there, then battery voltage gauge is there, then pressure gauge is there. Many informations are available from the car dashboard. And the cost of a car is about the minimum cost will be 6 lakhs and it can be more than that. But even in a 6 lakhs rupees car, we get many information. Similarly, the middle figure here is actually a SPO2. It measures the um, somewhat that oxygen level, and it costs only 2,000 rupees. Not only oxygen level, it gives many information in the small display, right? In comparison to these items, the civil engineering structures, this is a photograph of a building, Golden Jubilee building, that is, we spent about 100 crore rupees in 2013 estimate. Today, this building will cost more than 120, 130 crores. Similarly, any civil engineering structure, if you see any bridges, important structure or any important building, that cost more than 100 crores. But there is no instrumentation in this building. The user are not allowed to know the level of the stress that building is functioning and what is the maximum stress carrying capacity of the building. So even in the bridge, when we go in a bridge, many times outside it is written the bridge is not safe. You have to go high. Heavier vehicles are not permitted in this bridge. So some qualitative things are written in that, but there is uh, no instrumentation to give a quantitative measure of the safety of the bridge. So paucity of available instrument for civil engineering structures. So there is a question why civil engineering structures do not have such instrumentation, right? Now, in the construction, we can see here two figures, one in 1973, the other one in 2019. The problem was premature removal of formwork, because we remove the formwork based on the code guidelines that after this many days we can remove the formwork. But actually, we don't consider that what is the purpose of the formwork, whether the purpose is already met, uh, that we can get if we know what is the strength achieved by the concrete structure, and if it is sufficient to resist the shell point, or we still require the formwork. It requires the support of the formwork. So with the same problem, there was an accident in 1973, and there is again a problem in 2019. So in this many, about 50 years time, there's no progress. Still now we don't have any instrumentation in this concrete structure. So the bottom line is, uh, that automated real-time monitoring system are indispensable in the construction industry to significantly improve the productivity, quality, economy, safety, flexibility, and accuracy. So if we have to, suppose we had a instrument here which can give us the information that now concrete is sufficiently strong, formwork can be removed. Right, so we can remove the formwork in timely manner and improve the progress. We can go for the next lot of construction. But now we are bound to wait till the code guidelines that this many hours or this many days we have to wait before we remove the formwork. Sometime even after that, if the concrete is not achieved sufficient strength due to various reasons, because now we are doing a lot of experiments with the concrete, all the code formulations are based on OPC, cement and other type of concrete, but now we are mixing many admixtures and there are other mineral admixtures, some replacement of aggregates and replacement of cement with some other sustainable waste materials. So for that, the code guidelines are not always accurate. So we are seeing problems in the construction progress. So if we can develop a monitoring system, then it will be better. Now in this presentation I am concentrating the aspect of monitoring early age compressive strength of concrete at real time. The strength growth at the early age. Why early age compressive strength? Because the growth of the early age concrete strength is very critical to ensure the quality and performance of the structure in the later age of the structure. The stakeholders can save substantial time and money by accurately estimating early age compressive strength, which allows crucial construction procedures to be optimized, like formwork striking, opening of traffic or pavements, cable tensioning of pre-stressing member, and shortcut applications. For all these applications, if we can get accurately the growth of the strength, concrete strength over the time in the early age means especially the age before 14 days, right? That age we are thinking. Many factors like concrete and atmospheric temperature, the temperature within the concrete, because when concrete hardened, there are heat of hydration. In this process, heat of hydration, it's an exothermic reaction, and from the temperature we can know the temperature of the concrete, we can know what is the development of the properties, concrete properties, right? One is the concrete temperature, then atmospheric temperature, relative humidity of the atmosphere, wind velocity, etc. can alter the development of the early age properties of the concrete. Real-time monitoring of the above parameters. So if we can monitor, which is very easy, the concrete temperature, atmospheric temperature, relative humidity, wind velocity, etc., all measurable parameters using some sensor, then it will be very useful for knowing all the early age properties. It can be strength, it can be all other properties also. So that will be useful, very useful in quality control and construction management. With the recent advancement in sensors and microcontrollers and the IoT technology, real-time monitoring of concrete can be achieved with superior accuracy and with lesser cost. Now you see what is the traditional process that we follow. We make specimens, right? This cylindrical specimens, and we cure it on the field, or we take it to the laboratory and lab cured specimen, and then we break it at 28 days mostly, or 7 days. Therefore we get a delayed result. We don't get, so the results we are getting at the time the intervention is difficult, right? And it does not represent the curing condition properly, because these are cured in the laboratory, you see, under the water, but in actual structure curing condition is different, right or wrong? So the specimens, the specimens that we are testing, they are not representing the correct curing condition, does not represent the in situ concrete. So many times it so happens that the concretes which is there in structure are separately made, and the specimens are taken from separate mix. So they are not representative of actual concrete that is there in the structure. And there is another instrument is the rebound hammer test that is often used, and which has also a lot of, it only gives you the cover concrete, the strength of the cover concrete, and it does not say the strength of the concrete that is within inside, actual strength of the concrete that is inside the structure. Only at the surface layer strength we get from the rebound hammer. So even the code, design code says that reliability is plus minus 25%. So we cannot trust the value of the rebound hammer unless we do a core testing or many other testings in conjunction with this test. So now, if you see, rebound hammer is a non-destructive test which has a low accuracy. There is a penetration resistance test which is a destructive test that also has a low accuracy. An ultrasonic pulse velocity test, pull out test, they are also, you can see here, non-destructive test. UPV is a non-destructive, pull out is a destructive. They have a medium accuracy. Then we can take drill cylinder is a destructive test, or cast in place cylinder, again we break test. They have high accuracy, but as we have discussed that it is a delayed result we get, or we get result for non-representative specimens. Then there are some piezoelectric method and maturity method. They are all non-destructive, but it has certain degree of accuracy. And if you see, the real-time monitoring is possible using maturity method. There is a well-developed method, maturity method. It is already outlined in design codes, American code, and there is a model code, FEB model code. Many codes and standards, they have used this method for estimating the strength separately. Now, based on this maturity method, I am going to come and we will be discussing about the maturity method. So there are some maturity meters are available in the market. So what maturity does, it you have to take this instrument to the site. It calculates the, again from the surface, it calculates the heat of hydration, and maturity is a function of concrete temperature, right? Maturity is a function of concrete temperature, and this time temperature one function, this is related with the compressive strength in this maturity method. So you will using this instrument, you will go to the site and get the maturity, that is the temperature time history. From temperature time history we get that, and then concrete strengths are correlated. So this is also not a automated system. You require human intervention. One person has to go there and get the data and find out. So what is concrete maturity? You see here the temperature in the y-axis and time in the x-axis. So the integration of this temperature time history represents the maturity. So here this is M1. M1 is like 20 degree centigrade temperature, constant temperature over a 5-hour time. So 5 hour into 20 degree is 100 degree centigrade hours. This is the maturity. Here we have a constant temperature of 40 degree. This is the concrete temperature, internal concrete temperature, but over a time of 2.5 hours, it is also same maturity. So the maturity, same maturity, 100 degree centigrade hour for all three cases. But in the first case, it is in 5 hours, it is in 2.5 hours, and it is in 10 hours. So this same maturity represents, if you see in this curve, same maturity represents the same compressive strength. But in this case, in 5 hours, this compressive strength is achieved. Here it is achieved in 2.5 hours, and here the same compressive strength is achieved in 10 hours. So it is related to the temperature time history. So maturity is a concept that has existed since 1950s, a non-destructive method to estimate the strength development of in-place concrete, especially at early ages, that is less than 14 days. It uses the temperature history, temperature time factor of concrete to estimate the strength development. The compressive strength of hardened concrete is a function of the rate of hydration of cement and is proportional to the internal temperature time history of concrete. This is the primary assumption of the maturity method. So I have given here two relationships. One is proposed in ASTM code, that is C1074, and later on in the CEB FIP, this is European model code, where you can see the compressive strength is a function of maturity. It is in logarithmically related. M represents the maturity, and here it is an exponential. There is a TT instead of N, they write a TT. This is also temperature time factor, and with an R and FCM, these two another constant. Here A and B are two constant. Similarly here R and FCM two constant. Otherwise it looks the same function of M and this function of TT. M and TT are somewhat similar. So in the FIPCB code, FCM for a concrete which grade is less than 60 megapascal, we take the value R. They have given some values of R here for this code for different classes of cement based on European code, right? Now let us now see what is maturity. This is M and this TT, they are two maturity, and M is a summation of, we can make an integration of TCI, this is the concrete internal temperature, minus a datum temperature, one T naught datum temperature, into Pi, that is the time step. If you put an integration, then it will be a dt. Similarly here TT is the change in this time step into e power, this is the concrete internal temperature TCI, and again the time step. So if I now think this is easier for understanding, so in this method if I plot concrete temperature over time, so you see a temperature will be increasing at the beginning, then it will have a temperature like that, and then if we deduct, this is the TCI, if we deduct the datum temperature and this area, this is the integration of the curve, this TCI, curve of TCI minus the T naught and DTI. This area is the representation of the maturity. Datum temperature is defined as the temperature above which the hydration process and strength development of concrete are most likely to begin. So this is the datum temperature, right? Now, if we see, there is a procedure as per this code. So how to find out this datum temperature? It is like we have to make different set of, for a given mix. Suppose I make a M25 grade of concrete. I am going to test the M25 of M25 grade of concrete at site. So I will prepare the same mix in the laboratory, and strength edge relation of mortar specimen can be developed experimentally at three different temperature. So these are the three different temperature, atmospheric temperature. We create the compressive strength versus of this, and we get a different edge, and this is 1 by edge, and this plot numerically we can make, and we get the values, this y-intercept, we get the values of y-intercept. This is what is CT, and this from the CT, see this this arbitrary constant is calculated here. Intercepts of the ordinate of this plot is called the limiting strength, this S infinite, and this ST is the compressive strength. Here you can see this y-axis, So ST divided by S infinite minus ST. So this gets a C naught value, C of t. So at different time step, we get the value of CT. And this CT versus edge we consider here, and we get the slope K. So this is a practice. This is the flow of this rate constant K, and we plot that rate constant and where it hit the X curing temperature versus rate constant. We have three values: 10 degree, 20 degree, and 30 degree. Because these three values we curing temperature we have, and we get a datum temperature. If we don't calculate this datum temperature, code can we can assume the value 0 degree as a datum temperature, and here without deducting anything we can do also this maturity method. There will be some impurities in the result, but we can do that as well. So what is the problem? Now this maturity meter, I said, it is manual recording of compressive strength of concrete at the site by measuring the internal temperature. As this instrument is operated manually, frequent recording of internal temperature is cumbersome for real-time prediction of the compressive strength, because you have to frequently go to the site and get the maturity of the concrete, and then come to the laboratory, and you have to attach this device with the computer, and there is a software program. It's generally required by the conventional maturity meter to extract and analyze the data in computer, and it is also very expensive equipment. Now, to overcome this shortcoming, that means to automate this process, an IoT enabled setup is proposed for real-time monitoring of early edge compressive strength of concrete using the principle of maturity method. We can use either of these two methods. What is Internet of Things? Internet of Things is maybe a little complex, but what I understand is collecting data through sensors and actuators and send this data to a gateway, and from this gateway it goes to the cloud platform, and from cloud platform we can receive this data to any applications. So in that procedure, it automatically comes from your structure. You collect the data through device, and it sends to the gateway. Gateway receives the data, and then we can, in the device itself, we can calculate, or you receive the data in the cloud platform and put some in the platform. We can have some programming here which can analyze the data, and from there the ultimate output value can be available in any device through internet. So a network of interconnected devices that can communicate the data gathered from a monitored field through a wireless link, and human interaction is not required, machine to machine communication. This is what is Internet of Things. So broad methodology is, in this procedure we can determine the datum temperature through lab test. Just now we have seen there are some procedure given in the code. The datum temperature for the concrete of the grade which is going to come in actual structure. Now once we know get the datum temperature, we can develop the strength maturity relationship through again laboratory test, because we know that T naught now. After that we can do some more test in the laboratory and find out the values of here. See, this is the strength maturity relationship. In the strength maturity relationship, we have to find out the constant A and B for that particular mix. So if we take the maturity and do break test of particular specimen and make the relation using this model, we can calculate the A and B value. So we can have a relation between strength versus maturity. Once we have that relation, then we assemble the IoT enabled time monitoring system in actual structure, and we feed the strength maturity relation in the system, and then we get the data field deployment, right? So there are various types of communication technology. So you see, we require to communicate the data. So there are various technologies like RFID, Bluetooth, Zigbee, Wi-Fi, GSM, and LoRa. LoRa is like range. If it is only 10 meter, then RFID is fine. If it is only 100 meter, then Bluetooth works, and Wi-Fi, all are in this range. But in a large construction site, mostly is bigger than 100-meter side. Like in our, we are making our hostel buildings here. The project side is about 300 meter by 300 meter, one small project. So it requires long range communication technologies. So long range communication technologies are very, these two GSM technologies there, LoRa technology is there, and it has a cellular band, and LoRa has frequency range like that, and the energy consumption is very high, and cost is also medium for LoRa technology. So for that we have selected this LoRa technology in our experiment in this project. So the LoRa network like that. So we have LoRa end nodes that is there in the structure, and it transmit to gateway, and gateway it can receive. It is a two-way communication. Gateway can also communicate to this end node, and end node can communicate to gateway, and there is a you require a LoRaWAN server that is in the
I
yeah.
I have a question here.
Yeah, please, sir.
I have a two questions. First
Yeah.
question is about we have used I want to relate this question more or less. So
Yes, sir.
one of the first question is we have tried this one of our user case project in IIT Hyderabad
Yes,
for
sir.
setting up the CCC control command. Uh, where we are talking on IoT drone, but that couldn't work with the whatever you have shown in this study based on the frequency. So in that case, how do you interfere? Without my question is in complete detail. So how we can interfere, the resource without any people in site management using the CCC technique based on the frequency.
Yes, sir.
That is, could you answer or could you elaborate on that so we can have some?
No. You are asking the frequency range of this communication.
Not it's not about the complete frequency range. Suppose I have my say we coordinates. It's like, okay, so my site is located in Y coordinate. I have to track my resource quantity, whatever completely my construction site progress is going on. So
Yes.
there, we have set up a CCC center, control command center. So it's
Okay.
based on again IoT, where completely data driven is given to CCC. People will monitor there. So in that
Yeah.
case, we lost, the frequency, whatever you're talking in terms of levels between this level, Wi-Fi or IoT, that could not
Okay.
support. So do you think will IoT can help us or something, or further to that elaborate? I'll just answer
Yeah. Actually,
ask
sir.
you the second question.
No. Initially, sir, we were doing in the laboratory, and we were using only Wi-Fi. Using a Wi-Fi router, we could do the testing in the laboratory.
Yeah, because
Then,
the question would be my sites are related to all the program management jobs what we are doing.
yeah.
These are cross country piping because we cannot even travel to there is a kilometers of frequency. So in that way, how to address this how to address this problem and what is the ratification behind this? Yeah.
Yeah, no. What I understand is you have some sensor data that you wanted to transfer in the through web, right?
Excuse me, sir. Sir,
Yeah.
Sai Krishna, let me introduce Sai Krishna. Sai Krishna is working as a business development manager at Bentley Systems. He supplies the software, STAD Pro, and all that software and
Because
construction
we
related
do a
software.
lot of consulting and we are doing because this kind of problem I want your input and we'll work together and I want
Sai
your
Krishna, we'll have a question answer session at the end of the talk. So you can ask them at the time. We
so
will
because
we'll
the
proceed with
point why I
the
related
session
is this is the slide we got it, so I want
at
to
around
relate to that. Sure.
No,
5:30.
it is fine. It is an implementation issue. I will discuss about that, sir. What we faced in the laboratory and site. So in the using an Wi-Fi technique, we could successfully do the testing in the laboratory. But we thought to use the same Wi-Fi technique in the site. When we went to the site, then we had a similar issue. We are not able to monitor the data in a large construction site. So we
exactly, there are a lot of geolocations. We cannot even identify the track of geo points or geo grids. So in that way, how would IoT or how would this CCC could help us in framing the signaling? Yeah.
Exactly what CCC method you are using, I am not so aware. And this we have maybe this part, the LoRa implementation of LoRa part, we could successfully do in our campus. We had a construction project going on in the site, and we were able to catch the data using this technology. So we will discuss about that once I finish this presentation. So it's a low power. LoRa is a low power wide area networking protocol for IoT application. It was also giving us benefit because it requires very low power and it can go to sleep mode when it is not transferring data. So those type of benefits are there in LoRa. And from the LoRa on server, it can go to the any application server like mobile phone, computer, where we can get the data. Now, what all things we used? We used a temperature recording sensor. The name of the sensor was DS18B20. It is a digital waterproof one-wire interface. It is something like that. And some data we can see here. It is a temperature sensor. It has a range, temperature range. It can record from -55 degrees centigrade to 125 degrees centigrade. It has a capacity, but although we don't require so wide range, and it has accuracy of ±0.5%, and sampling interval can be 0.75 second. In each 0.75 second, we can get the data. Body size is 4 millimeter diameter, cylindrical. This is here it is, and operating voltage is this much. The degradation in the signal over long distance is well within the limits. So the degradation also we have checked. And we have tried another sensor which is SHT10, and we have got the temperature of concrete and found relatively identical data from both the sensor. That's how we thought that they are recording right. So the accuracy of the temperature data that has been recorded by the sensor, we felt it is right because the differences are within 1% by two different sensors. And we require a microcontroller that will analyze the data. So we used an ESP32 LoRa microcontroller, and we used a LoRa 1 LG01N gateway, and this is the your sensor, temperature sensor, and this some of the specifications are given there, and there is one OLED LED display here itself, and the operating voltage is like 3.3 to 7 volt. And LoRa end node, this is a LoRa end node. It looks like that, and this is a sensor, and this is the sensor without the case, and with the case it looks like that, and this is actually the sensor. This is the end node, and then this is your gateway, and this is the actual, you see, handheld thing in the this is the instrument that we have developed. And this is in the end node we have a temperature sensor and a microcontroller and solar energy harvesting unit. So energy, we don't have to power it, it can find out power from the solar power, and there are some of the details here. And this is the solar power on harvesting unit and all that. Battery, lithium battery, which is charged from the solar power, and that will work here. And now the methodology for early edge strength prediction method. So we have inside the concrete, we have embedded that sensor. You can see here, this sensor is connected with a LoRa end node which is powered by solar panel, and it has a it can transmit from the end node to the gateway the data, and from the gateway it can go to the network server in the internet, and from internet anybody can see the data from the internet by logging into that particular site. It can be in the mobile phone, it can be in the computer. What it does, this concrete record the concrete temperature versus the edge. So temperature time history it creates. From the temperature time history we have to calculate the maturity, then the maturity versus edge, maturity time history, then from the maturity time history we get the concrete strength, because strength maturity relationship, using the strength maturity relationship over the edge. So working principle, the prediction of early edge strength requires the strength maturity relationship of the given concrete mix. This relationship for the given concrete mix must be calibrated with the actual strength data for accuracy, and this temperature sensor records the internal temperature of the concrete in real time and sends the data to microcontroller, LoRa microcontroller. Microcontroller calculates the early edge compressive strength based on the developed strength versus maturity relationship for corresponding concrete mix. So then a IDE, Arduino Integrated Development Environment is used for programming, because we have to use temperature time history to calculate maturity and maturity strength maturity relation for the. So all these things are used by a C programming using this in the microcontroller that was fed in the microcontroller. A new channel was created in, actually we have used thingspeak.com, is a free network server, and in that field temperature data, maturity index and early edge compressive strength data will be fed. And ESP32 LoRa microcontroller shows the data. We can also see the data in the site itself through a OLED display, and this data as well as can be available in the thingspeak.com, that your web server also, cloud platform, in real time, and that can be accessed from any remote location. So first thing is the calibration at the laboratory. As I said, that we have to calculate your T naught, that is your datum temperature, as well as strength maturity relationship, that A, B constant we have to calculate in the laboratory, and after it is done, then we can do a field deployment, and then we develop this, we get all the data. So this experiment we have done in the laboratory by using some particular mix of concrete. The cement values, details of the cements are given here. Details of the aggregate, coarse and fine aggregates are also given. We have mixed them, and the mixed proportion was used from some of the literature, some standard mixed proportion, that is cement is 438 kg per meter cube, fine aggregate is this much kg per meter cube, and coarse aggregate and water. And we did break test at different edge, and we got this is the strength. So FC versus strength and edge relationship, and maturity and edge also calculated in the laboratory. Then this maturity versus this strength are correlated, and A and B values are evaluated. So if you see the photographs, this is the, you see 1, 2, 3, 4, 5, and there are 6, 7, 8, 9, 10, 11 specimens are created, and in one of the specimen this sensor is inserted, and this specimen is shown here, where we have the sensor, temperature sensor is inserted, and LoRa node is kept here. So using this LoRa node, it keep on getting the data, temperature time history, and from this temperature time history data it calculates the maturity, and maturity we can see here in the OLED display, and also we can see in the web portal. And maturity at a particular time, when we see the maturity and we do the break test also, like this, after a certain age we see what is the maturity, we do the break test and we find out the strength. So strength and maturity, that data we keep, and then using this strength maturity data we make a relationship. So 18 cylindrical concrete specimens of each mix are cast, temperature sensor are inserted in the fresh concrete for 3 cylinders. So this is one side is showing. So in 3 cylinders are this was inserted, and the maturity data are received from this 3 cylinder, and average maturity data was recorded, and all the 18 cylinders were placed for curing in a water bath. 3 concrete specimens from each concrete mix are tested in compression testing machine after 1 day, 3 day, 7 day, 14 day and 28 days of curing to determine the actual compressive strength. And ESP32 LoRa microcontroller receives data from this sensor and automatically computes the maturity indices. So you can see these 3 things set up, and after the test, at the end we broken that. You can see here the sensor was inserted here, and so this is the one schematic diagram that we have. We have the curing tank, and we get all the maturity methods, and then this is the laboratory setup and maturity progressing, how maturity is progressing over the time we can see here. And then we can do a plot like that this is the test data at different age maturity. We got 1, 2, 3, 4 point, and from there an approximate value of A and B are calculated. A, this is FC is equal to this much megapascal, and this much megapascal into log times log maturity. That relationship, ASTM method. So now, if you can see here, we can see all the information is coming here. Maturity in degree centigrade in days 75.2, strength is 8.4 in megapascal. This much megapascal. So how strength is in STM standard this procedure, we can see how strength is progressing. So for validating, after we got that data, we did this test, repeated this test, and we found the actual break tester. This is the predicted values as per this equation, and experimental values are given in this small boxes, so it matches very closely to the actual compressive strength. And this is for one mix. For another mix, we can see again we have used here both the method, and it gives you quite a good agreement with the actual strength. Now you can see the errors are in this the actual compressive strength and predicted compressive strength, and you see errors are 8%, 6% and 3% in that range. Now we have deployed it in the field. This is in our campus. The gateway was kept in one of the building here, and it was it may be around 1 kilometer to 2 kilometer A, B. So we have seen here, you see the gateway was placed here, and our end nodes were placed at A, B, C and D. Is 500 meter, 1 kilometer, 1.5 kilometer, 2 kilometer and 3 kilometer in this much distance, right? And we know we have already discussed, create a new channel in the thingspeak.com where these values field will be there: temperature field, maturity index, early age compressive strength. These 3 fields are there. Assemble this IoT based system. That means it is a LoRa end node with a temperature sensor and a microcontroller and a flash C program there. And then in the execution stage, we are doing a strength maturity in the laboratory relationship, power the IoT based system, and in the laboratory we are doing that. And finally, we are coming to the real-time monitoring. So in this 3 phase, it is coming: initiation stage, execution stage, and monitoring stage. And we see the comparison. This is the maturity meter that is available in the market, and this is what is the system that we have developed. And this is the display we can see here in a enlarged view, and it is very much cost effective. This IoT based, price per unit in US dollar will be about $200, where the other market the devices available in the market are more than $1,000 cost. and it has a lot of other benefits. Real-time monitoring is missing here in these two instruments. Now we have used this thing now to particle format stripping. You know, in the standard, different international standard for particle formwork, when to strike of the striking time of the particle formwork. In different code says it is from 9 hours to 24 hours, right? And these are all based on the OPC cement concrete. But in the recent development of concrete technology, we are using PSC, fly ash, silica fume, GGBS, many things we are using. So if we still stick on to that time, sometimes there are problems we are facing in the construction site. So also these are the time given in the code. Codes are also giving, codes and different literatures are also giving that what is the minimum strength required before we remove the formwork, vertical formwork. So it says that 2.5 megapascal to 10 megapascal. This much strength when we get, we can, these are given in some of the research papers. So in the strength maturity index, you see this is developed in the laboratory, and we have already shown, I have shown you that information, that it is the strength maturity relationship are developed. This A and B values are developed, and datum temperatures are also developed. And we have done some laboratory tests where the columns are cast with the vertical form, and one of the column, and yeah, all the columns we have put that LoRa and node here, and we are getting the data from LoRa and node, and LoRa and node telling us when to remove the formwork. Now you can see here concrete temperature data is coming like that, compressive strength data is coming like that. This is the temperature time history, this is the strength time history. So strength is progressively increasing from 0.69 megapascal to some typical data 1.18 megapascal. And if you see the strength versus age, this is in very small time interval, but if you see in a large time interval, if you see the strength started, the point of strength initiation, it is about 11 hours. After 11 hours, the concrete started actually increasing the strength. And if you see the removal of a formwork, the visually how the column looks. We have removed the formwork at 13 hours for this column, 15 hours in this column, and 17 hours in this column. Now the strength results, actual strength, we have also had Q specimens of this same concrete, and at the same time when we removed the formwork, we have taken the cube strength, and the cube strength data from the strength break test, we got the data of compressive strength like 0.22 megapascal, 0.74 megapascal, and 1.19 megapascal at 13 hours, 15 hours, and 17 hours. And what was predicted? Yeah. Any question?
Yeah, are you comparing because when I'm observing this, are you comparing, the form finish structure of the column also when time is elapsing?
Yeah, this is the at 13 hours when I removed, we got the this is the visual representation of the surface, concrete surface. It appears that it is not fully set at this moment, right? But at 15 hours when you remove, same concrete is cast in 4 different.
You mean to say the time is increasing, the finish of the setting is also getting good? Yeah.
Right. When time is increasing, setting is better, right? And then at that time when I remove, I am checking what is the strength achieved. So this is the actual strength available from the break test, and this is the strength that we are getting from the LoRa 1 device, what the device that I said. So we saw in the early age, very early age, 13 hours, we see your deviation is little high, but as age is increasing in terms of hours, in the higher at 17 hours, the error is very small, but the values are not very different. Now, we have seen another paper, Santhanam and Gettu have reported that non-load bearing formwork can be removed from the concrete members once the concrete reaches the final setting. And final setting, final set is defined as the time when the penetration resistance is this, as per this 403 code. So we have tested that in the laboratory, that penetration test, and we have seen when that 27.6 megapascal penetration resistance is occurring. This is the age in minute, and at 15 hours we found the same concrete mix that achieves a penetration resistance of 27 point. It is like you free fall a penetrator here, as per this code there is an equipment, right, penetrometer. When we see 27.56 megapascal, this actually is something like 15-hour test. 15-hour at 15-hour time we achieve that penetration resistance, and so as per this literature, that is the time when we should remove the vertical formwork, that is the non-load bearing formwork. So here we see at 15 hours gives a reasonably good surface and it looks like it is set, and at that time about 0.74 to 1 megapascal strength is achieved by this concrete, right? So we can actually now if you see, look at the code once again, you see it gives you recommendation from 9 hours, American standard says 12 hours, British standard said 12 hours, and there are some other codes that says 24 hours, and our Indian code says 16 hours when we can remove. But this data again based on particular type of concrete. Now here for a type of concrete that we use, we can exactly see what is the strength achieved by the concrete, and we can remove judicially at a proper time, not very late and not very early also. So apart from this stripping of vertical formwork, this method can be used in different other ways, like stripping of horizontal formwork, load bearing formwork, monitor curing condition for plastic shrinkage. You know, many times at site curing is not done by the contractor, but that information is not reaching to the construction manager. But if we can use this system at site, we can, in our mobile phone, you can see an alert when it requires curing, when it is having plastic shrinkage cracks are impending, right? So that information we can get. Also, in an academic setup like us, we can do many laboratory tests without the help of expensive laboratory equipment. For many tests we require laboratory equipments that are very expensive. Due to paucity of sufficient fund, we are not able to buy this equipment. But indirectly, by measuring some of the parameters, we can get many data, right? So one such thing we have done is the plastic shrinkage crack. You know, plastic shrinkage occur when evaporation rate is larger than the bleeding rate. So we don't have sufficient water in the top surface. Because of evaporation, whatever the bleeding water is, bleeded water will be evaporated, and there will be plastic shrinkage crack. And this plastic shrinkage occurs usually in less than 8 hours, forms while the concrete is still plastic. So now for this we have some nomographs in American ACI code, right? American Concrete Institute, ACI 305, this code, where it has related with the concrete temperature, R is the relative humidity, TA is the atmospheric temperature, and wind velocity. All these parameters, this concrete temperature, relative humidity, atmospheric temperature, and wind velocity, they are measurable by using sensor. So if we can fix those sensors and get the value data, and using this relationship, we can find out what is the evaporation rate. And it says that if evaporation rate is less than 0.05 kg per meter square per hour, there is a less probability of occurring plastic shrinkage crack. But if evaporation rate is greater than 1 kg per meter square per hour, there is a high probability. So if we can find out that E value, if we know the E value, we know there is a problem. So we have again set up another device where we have a wind velocity one sensor and atmospheric temperature and relative humidity of the atmosphere and the concrete temperature. So all that together we can find out. So here we can see there is one, it's a LoRa microcontroller, and with the microcontroller we have to have this sensor of taking temperature. There's another sensor of taking atmospheric temperature as well as the relative humidity, and another sensor for wind velocity. So if we club together, it becomes a end node for us, LoRa end node. And we created, this is in the laboratory, although we have not tested in the site, we created some atmosphere to actually force the plastic shrinkage crack here. And we can see the cracks are occurring in the concrete due to adverse atmospheric condition created artificially here. And then we can see the small plastic shrinkage cracks are occurring, and then how well these are the ACI method, and there is another Menger method. There are two methods we were discussing here. One is here, one is the Menger 1954 one equation is there, another equation is there by ACI 318. So both this equation, once you have the data, we can use them in any equation, and then using this relationship, we will before any plastic shrinkage crack, we will know, and we can take an intervention study there. So we saw that there are two different methods. We have seen here that how rate of evaporation and time history is increasing, and this is an instant A, B, and C, and we also get an output voltage. There is two different systems we created here. There is one in the Menger method, what is relying on the output voltage. So we can see that at point C, evaporation rate is increasing, and here output voltage is dropping because due to the lack of water in the top surface, the bleeded water, the output voltage was dropping here. So using this technology with less cost, we can make a lot of interesting device that can be used for real-time monitoring of early properties of concrete, which is also cost effective, right? So with that, I'm stopping my presentation here, and I want to acknowledge the student who did all the work, PhD student Semin. Thank you very much. I think I have taken little extra time. If you have any question now, if possible, I will respond.
Audience, please ask questions.
Yes. If
Sai Krishna, if you have any question, you can ask.
No, I think I have to talk to him in separate in implementation perspective.
yeah, implementation, right, sir.
One more thing I saw, because you're talking on plastic shrinkage cracks, because we see, excess water or even into excess weightage of cementatious gel,
Yes,
calcium silicate gel, CS gel,
right.
agglomeration formation.
Yes,
Do you think this kind of chemicals, adding external additives or admixtures, like kind of chemical or mineral admixtures, will support or reduce the physical shrinkage cracks like this?
Yes. Actually, there is I have seen they have a white color, some layer, because the places where curing is not possible at all.
Because why I raise this point is especially in terms of long sites, the batching
Yes.
plan would be in other place, and when we are doing the especially we need to consider this in terms of what we understood is in doing especially in top roof slab, especially in waterproofing works.
Yes, right, sir.
Because there is lot of cementanish content, and concrete from other batching plants is getting affected to the sites which we are placing in geolocations. There, the initial setting time or final setting time of the concrete could not be set, so that the RMC, which is coming across the place to supply the concrete, we
Yes.
are facing this kind of facing. I think there are some few companies called MBCC Group. We have done some work with MBCC and Klimas. There
Right.
are other companies called Fishner, who has
Yes.
good, additives to reduce this physical shrinkage.
Yes.
Yes,
Yes.
so plastic shrinkage.
Right, sir. Right.
Sai Krishna, you can interact with sir on you can get his contact number and you can discuss with him and see what you can go progress further.
Yeah, especially in the CCC, I want to talk digital twin. I'm
Right.
just relating how we can link with digital twin and we can connect as a CD and more,
Okay.
especially in site operation perspective. Yeah.
Right, sir. So thank you,
So,
sir.
more
Thank you very much.
questions?
Yeah.
Yeah. Thank you from our side, sir. It was the best was saved for the last. I think we are very much impressive work you have done. You have combined two fields, the civil engineering field and the Internet of Things and making useful applications. So I think speaker, I think no more questions. So thank you once again, sir,
Thank
and
you.
we will conclude this session. Uh, this brings our course to a conclusion. So if participants can share their